Going. So let's continue. That's a quick half-minute break, right? Okay, so I'll give you 2 examples in the next 40 minutes or so, and then we should be good. So the whole thing we have learning is, don't forget, we have fixed both ends. Displacement is 0. Okay, so let's see how we can use this condition to solve for some of the problems that's typically happening, but it's without this we cannot solve for it. Okay. All right, so let's see here. So first example. So example 1 is nothing but very simple and similar to what we learned. Okay, let me write it. Determine the support reactions at the rigid support A and C. The 2 rigid supports supporting points, in other words, A and C. Okay, so the modulus of elasticity is E. In other words, Young's modulus is E. Okay. All right. So a simple problem. Fixed end. You have a rod, relatively speaking, large diameter. Then comes down to a smaller diameter, and also fixed at the end. Okay. Now there is one force being applied right at the section, right at the interface where these 2 rods connecting together, right? Let's say this is force P. Alrighty, so this is my point A right at the end. This is point B. This is point C. Okay, so the distance between A and B is 2A. And B and C is A. So AB is twice the length of BC, in other words, okay? Now, the diameter here, they're both cylindrical, okay? So this is D. This is 3/4 times D. Okay, already, and then that's it. One force being applied, and then asking for what is the reaction force on point A, let's say FA, and FC. But I don't know where the FC and FA is, but chances are once I do free body diagram, I can find it, right? So simple problem, okay? So let's see how we can do that. Now, first thing first, free body diagram. This is fundamental of all the things we learn, okay? So free body diagram, let's see how it goes. So we will have a section AB, and we also have section BC, right? So here we have force, that's P over here. Now, just like the 2-spring system, remember we mentioned, so just like that, and then there's another spring, there's a force that's going there. So we know the chances are this spring is under compression, this spring is under tension, right? So therefore, the force going up that way, FA, and there's force going that way, which is FC. So chances are this section over here is under compression, this section over here is tension, right? So very simple. Help you to understand why FA and FC both goes to the left. Okay. Now, if not, if you can imagine that without a 2-spring, that's fine too. It doesn't matter. But I think the 2-spring will help you to understand the direction of these direction force. Okay. So FA and FC both go to the left. Alrighty. So let's see the conditions here. First of all, the length is 2A and A. Okay, so let's don't forget that. And here you have diameter D, diameter 3/4D. Okay, all right. So you have 2 different sections of the rod, and then we also know, important, let's put this right here. So don't forget, delta A is equal to 0. Why? Because look at here. point A, point C, right? So, because both A and C are fixed, of course, the displacement between A and B is 0, okay? Alrighty, so let's see how we can do it. Now, first of all, we have this free body diagram. We have 3 forces. 1, 2, 3, okay? 3 force, that gives you summation F is 0, so therefore P, the force going to the right, equal to the force going to the left, Fa plus Fc, right? Left force equal to right force, okay? Don't worry about positive and negative, like I said many times, okay? Alright, so this is my equation number 1, okay? We need one more equation to solve for the Fa and Fc, right? So chances are we know we're going to use this condition. Alright, so let's see. Delta AC is equal to 0, right? And AC, we know, is nothing but from point A to point B to point C. AC is nothing but AB plus BC. Now, chances are AB is undergoing tension, so positive displacement. BC is undergoing compression, so negative displacement. Okay. All right. So once we have that, then the next thing becomes also easy. We need to find out what's this and what's this, right? Okay. So another thing is, let's see, the free body diagram of the whole thing. Let's see here. It's something like that, right? So delta AB and BC. If you want to know what's the displacement, we better know what's the internal force, right? So let's look at AB. Let's assume we cut right here, okay? And then this force is Fa, I say, right? Now there's got to be another force, which is Fab, internal force. Now, what is Fab equal to? Yeah, you guessed, Fa, right? It's just the same magnitude as Fa, but different direction, point to the right. Because summation F has to be 0 for AB as well, right? Okay, so for the section of BC, you do the same thing. So you can cut right here, okay, very close to the interface. Now this, wrong direction. This is my force FC, and I have to have another force FBC, and the FBC has to equal to what? Yes, you guessed that again, right? Equal to FC, right? Same magnitude, different direction. Okay, so another internal force right here, right here. So problem should be easy. Now, like I mentioned, delta AB plus delta BC is 0. And this is positive displacement, AB, right? As you can see, under tension. And BC is negative displacement, as you can see, under compression, right? In other words, I say AB and BC has to be 0 for the absolute number, right? Remember what I just mentioned? Because I really hate to deal with positive negative signs because these are just mathematical problems, and for us, everything is physical, right? It's either a positive or negative displacement means tension or compression. So I would rather just deal with the numbers, not the signs, okay? Because I know what does the sign mean. This means tension, this means compression. So, okay, so let's do that. Delta AB is nothing but FAB, LAB divided by AAB, EAB. That's just the standard definition we learned 2 weeks ago. Remember? Okay. The other one is nothing but FBC, LBC, and ABC, EBC. Okay, alright. So, something we already know. AB and BC, they're the same material, so therefore the Young's modulus, what? They are the same, right? Okay, perfect. So they just cancel each other. All right, one less parameter to deal with. Okay, plugging all the other unknowns. We know FAB is equal to FA, and we know FBC is equal to FC, right? Right here, look, okay? All right, so LAB, length of AB 2A, right here. See here, AB is 2A, and BC is A, right? And LBC is A. Okay, now AB is nothing but pi over 4d squared. And then BC, cross-sectional area of BC, is nothing but pi over 4. Now this time the diameter becomes smaller, 3 over 4d squared, because right here, look, one of the diameter is d, the other one is 3 over 4d. Okay? Plug everything in. Okay? Then we should have our ultimate equation. So let's see here. Plug it in. Okay? FA times 2a divided by pi d squared divided by 4. That should equal to FC times a divided by pi over 4, 3 over 4d squared. Okay, already, so lots of things can be cancelled. A, and then pi, and then of course d squared later on, right? So you do the math, so I can find out this say, oh, 1 over 4 as well, cancelled, and then d squared cancelled. So all I have is 2fa equals to FC divided by 9 over 16. Okay, so I will know FA equals to 9 over 8 times FC. Alright, just divide by 2 on both sides of the equation. Alright. Okay, finally, I call this equation 2. Why? Remember we have a equation 1 over here. Okay, 2 equations, 2 unknowns. You can do what? You can solve for it, right? Okay, so let me write equation 1 right here since it has been a long time. 2 equations, 2 unknowns, we can solve it, right? So plug 2 into 1. So in other words, P equals to 8 over 9 FC plus FC. Then we know P is a constant, by the way. It's a force being applied, right? It's not a variable at all. So FC is 9 over 17 P. And then this FA is 8 over 17 P. Plug it back into 1, okay? Okay, so this is our answer. So yeah, it's very straightforward, right? It's only this equation 2 takes a little bit of time to get it. Okay. All right, so that is how we solve for it. Now, this is relatively speaking a simple example, right? It's not that hard. The only thing you have to be careful is you have to know how to find the second equation, right? The second equation is very straightforward as well, actually. Just displacement equal to 0, okay? Alrighty, so that is that. And I guess the drawback of a virtual lecture is I don't get a feedback from you guys. You guys cannot ask any questions. But I guess if you have any questions, hold on that, okay? And then on Tuesday when I come back, you can ask me any questions you want, okay? So let's just move on. I'll give you one more example, and then we'll be good, okay? So let's look at one more example, okay? So we have a aluminum rod AC is reinforced with a firmly bonded steel tube BC, which I'll show you the figure later on, right? Now, if the assembly fits tightly between the rigid support so that there's no gap at C. All right, determine the support reactions when the axial force of 400 kilonewton is applied. So also one last condition is the assembly is attached at point D. Okay, so it's a little bit more complicated than that, but it's not that bad. I'll show you, okay? Alrighty, so there's a ceiling of point D, and we have a, first of all, not very straight, we have an aluminum rod AC all the way to the bottom, okay? Alright. Okay, so AC is aluminum. Let's say the starting point of the rod is A. Of course, as you can see, A and D, they basically the same point. Basically, D is just a ceiling, okay? A is the starting point of the rod, and C is the end point, okay? Now, from point B, there is another stainless steel tube that's wrapped around this aluminum tube, or let's say rod, tightly. All right, so basically that's rod in rod. Okay. All right. So therefore, in this section, you would imagine, which I draw you a cross-sectional view of the section BC. This is the point B, right? So BC really, if you look at here, using your graphics knowledge, this is AA cross-sectional view. So it looks like this is my aluminum, and on the outside I have my stainless steel. Okay, so we have these two. So basically these are concentric cylinder setup. Okay, aluminum in the middle, then you have a stainless steel shell. Okay, all right. So this is my aluminum, then this is my steel, and also give you diameter informations. So the diameter of it's hard to draw now. The diameter of the stainless steel is 50 millimeters. The diameter of the aluminum is 25. Over here, 50 millimeters. So in other words, steel has diameter of 50 millimeters. And then the aluminum, which is internally, I guess it's getting hard to draw for me. So I'll probably just do something here, right? And I'll write over here, diameter is equal to 25 millimeters. Okay, all right. So smaller diameter aluminum, big diameter steel. Okay, so let's just erase that. So therefore, you know what does that mean. Okay. Alrighty, and also the height information I didn't give you, which is right here. You have 400 millimeters. Then you also have a 800 millimeters of bottom section right there. Okay, the force being applied is right on point B with a magnitude of 400 kilonewtons. And this is my view of section AA, by the way. Don't forget that. Okay? Alrighty. Okay, so now one more thing be clear is the aluminum and the stainless steel here, they are tightly close to each other. Alright, they are the snag fit. So therefore there's no slippery or there's no displacement relatively speaking from aluminum to the steel. Okay? Alright, so one more condition is Young's modulus of steel is 200 gigapascal, and the Young's modulus of the alloy, the aluminum alloy, let's just say Al, is 73.1 gigapascal. Okay, already, and then let's see how we can solve for that. Now, all this problem is asking is determine the support reaction when the axial force is applied, right? So the support force is what's really asking. In other words, again, force at a D and force at a C, right? So at D and C, okay? Just like the previous problem. But this is a little bit more complicated because there's more materials, right? Okay, so let's see how we can solve for that. First of all, let's lay out all these given conditions. L, A, B is nothing but 0.4 meters, right? Length of AB, okay? And AAB, cross-section area of AB, is nothing but pi, and then pi r squared. Oh, sorry. I think this condition I gave you wrong. This is not diameter, this is radius, okay? Apologize for that. So pi r squared, then that for aluminum, because AB is aluminum, right? It's equal to pi times 0.025 squared. Okay, transfer that to meter squared, because later on, the displacement I want in meters. Okay, now also EAB is Young's modulus of aluminum, that is 73.1 gigapascal, and then this is everything for AB. Okay, then I also have L for a section of BC that is 0.8 meters long, and ABC for the section of aluminum, because BC section is complicated. Remember, there's a aluminum in the middle, then you have steel as a shell. Okay, so that is pi 0.025 square. That is also, we can transfer that to meters, just be careful. And then this ABC, which is the stainless steel part, that is pi 0.05 square minus 0.025 square. Basically, outside minus inside is whatever left for the shell, right? Okay, so also meter square. And there's two more things. EBC in the aluminum core section is 73.1 and times 10 to the 9 Pascal. If you want, use gigapascal. It's the same thing, just like before, right? Or this EBC stainless steel section is nothing but 200 times 10 to the 9 Pascal. Alright, so that is it. This is given conditions. Alright, so first thing first, free body diagrams. That's something always important. Now let's look at it here. So we have a smaller section of a aluminum, and then let's use red for stainless steel. They fixed at both ends, right? Then this section, FFD, and at this point I have my force being applied, which is 400 newtons. and I have this section. I have FC, but that's aluminum portion, and also I have this another force. I mean, really, there's a force always around it, right? I write 2. Let me use a different color actually. That's better. Okay. Let's say it's everywhere, okay? So let's just say this is FC, stainless steel part, steel. Okay, all right, so this is what the free body diagram looks like, right? Okay, so using this free body diagram, automatically we have one equation can be solved. The force going up, FD plus FC, the aluminum portion plus FC, the stainless steel portion, that should equal to what? The force going downwards, which is 400 newtons. Oh, so 400 kilonewtons. I forgot to write K over here. There you go. Okay, 400 kilonewtons. Kilonewtons. Okay, all right, so this is what it looks like. Now, three unknowns, one equation, we're like far away from being able to solve it, right? So how do we solve for the other two? Immediately we know FCD is 0, right? So that's something we can do, okay? So let's see what's the other one we can do. Now, FCD is 0, in other words, see here, we have a the top section right here. Then let me draw it the other way. There's aluminum and there's a stainless steel. Then we have the force going downwards. Then we have this force, and one more force from the stainless steel, right? Now, if you look at these two in two sections like we always do, right? So whatever displacement here plus whatever displacement here, they should equal to 0, right? Okay, so let's see how we can solve it. Now, just be consistent, A, B, and C. In other words, I mean, like I mentioned, A and D, they're the same point, right? Because D and A, they are just 1 point. So in other words, delta AC is 0. So that makes you think AC is nothing but AB. Should equal to that, right? AB is under what? Tension, that's right. BC is under what? Compression, that's right. If you don't understand why it's tension compression, think about these two spring system again, okay? So AB is one spring and the BC is another spring, right? The force going down, of course, the top spring is under tension, the bottom spring is under compression, okay? Same thing. So let's see here. Oh, I think here's another thing. Now, BC and AB, BC which contains both the aluminum and the stainless steel, right? Well, AB only has aluminum, so be careful on that, okay? Alrighty, so let's see how we can solve for that. Free body diagram for section AB. AB, this is my FD, this is my FAB, so you know FAB is nothing but equal to FD. Same magnitude, different directions, right? Okay, my bottom part is complicated, so we have, I need a red color by the way. So maybe the top I can do this. That's right. Okay, now the force in the bottom is nothing but equal to FC aluminum, and also there's another force that's in red color supposedly, which is FC stainless steel, right? Okay, now this reaction total force over here should equal to FBC. So therefore, FBC is nothing but FC, aluminum, don't forget this term, plus FC, steel, right? Okay. All right, like I mentioned, we have three unknowns. As you can see over here. FCl, FC steel, and FD. So we still probably need one more, right? So the other one is, I say, delta EC aluminum equal to delta BC for stainless steel. Agree? So what does that mean? In other words, means in the BC section, because aluminum and steel, they're tightly bound together, so displacement should be the same. Now, you don't believe me, or it's hard for you to understand? Think about this, because they're bound together, right? Just like two springs. Now, if there's force applied on both sides of the equation, this one's K1, this one K2. Now, K1, K2 are different, just like aluminum and stainless steel have different Young's modulus, right? I ask you, what is the displacement of K1, let's say delta X1? What is the displacement of K2, which is delta X2? What is the relationship between delta X1 and delta X2? They have to be the same, right? Because these two springs, they are in parallel connection, so the force being applied causes the same amount of displacement for the two springs. Okay, so same thing for that aluminum tubes, aluminum rod and steel tube, right? Because they're bonded together, they have to see the same amount of displacement. Okay, alrighty. So this gives me one more condition. So, three equations, three unknowns. We should be able to solve for it. Okay? Alrighty, so let's see how that goes. So first of all, equation 2, I think that's everything's clear already. So let's do that. Equation 2, that's delta AB is delta BC. Okay, so FAB, LAB, AAB, EAB, BC, that's a from point B to point C. So therefore, FBC, LBC, then ABC, AE, BC. Can't write C here. Okay, so that is my answer right there, right? So it shows you how the displacement is equal to the same. Now remember, in the beginning of this class, we showed in the beginning of this example, I showed you how these four parameters are quantified. All right, so once you plug it in, you should be able to find it. So let's do that. So FAB times 0.4 divided by 73.1 gigapascal, okay, and then pi times 0.025 square, that is equal to FBC times length divided by A BC, which is the same amount of Young's modulus times the same amount of cross-sectional area. Okay, now here's the important. AB and BC are the same, right? We also know the displacement of BC. So basically, there's two parts. One, the displacement of the aluminum in that section, in section BC, right? And the other one is the displacement of steel in BC. They are the same. So whichever one you pick are the same. In other words, if you don't quite understand, again, the two-spring system, force, delta X1, delta X2. K1, K2, right? So delta x1 equal to delta x2 equals to the total delta x, right? Because whichever one you pick, they are the same amount of displacement. Make sense? Okay, this is how we solve for the spring system, right? So therefore, you can use either one of that. I just use the aluminum because that's easier. So therefore, I can cancel everything in the denominator. Make sense? Okay, so all right. If some of you don't understand, we can have a question and answer session after I come back on Tuesday, right? But open your physics book. It's very straightforward for springs. Okay. All right. So therefore, I have FAB is equal to 2 times FBC, right? Okay. So there's one more equation right here. Perfect. Okay. Then the next thing is also we want to know one more, right? The one more is right here. So equation 3, aluminum and stainless steel have the same displacement. Okay, so let's solve for that. Stainless steel, FBC from equation 3 by the way. LBC is EBC and ABC for stainless steel. That is equal to FBC, LBC, and EBC, and then ABC for the materials of aluminum. Now, in this case, modulus and the cross-section area, they're all different, okay? The only thing the same is LBC and FBC, right? Okay, so therefore, FBC are not the same because the force applied in the aluminum and stainless steel are different. They are different, okay? All right, so let's plug that in. FBC times LBC is 0.8 and EBC is 200 times 10 to the 9. ABC is pi 0.05 square minus 0.025 square, and then FBC in the aluminum section, stainless steel, aluminum 0.8 divided by 73.1 times 10 to the 9 multiply pi 0.025 square. Okay, already. So therefore, there's another equation, but we only have a BC in the stainless steel and aluminum. Okay, so in that case, we have a force in BC stainless steel portion should equal to roughly about, if I did my calculation right, about 3.2 times of FBC in the aluminum. Okay. All right. So once we have that, then we can have all the things being solved. Okay. So first of all, this FC, which is bottom part, right? FC in the aluminum plus FC in the stainless steel, that should equal to roughly 9.2 FBC in the aluminum. Okay, this is when you have these two things solved right here. Okay, so see here, FC aluminum, FC steel, right? Then we have aluminum and a steel. Once we plug that thing, let's call this equation 4. Plug 4 back into 1. This is what you have, okay? And then we also have this. Let's say this is my equation 2, 4. Let's say this is 5. So coupled with equation 5, then you should be able to solve for all the things that's unknown, okay? So therefore we have FD, that's 71.4 kilonewtons. And FC is FC aluminum plus FC stainless steel, then that is equal to 400 minus FD, okay, times 10 to the 3, don't forget the kilonewton. Then we have answer Fc equals to 328.57 kilonewtons. Okay, already. So that's how you solve for it. Okay, the reaction force at the C. Make sense? Right, it's nothing but actually these two forces